Hey guys, so in today's video we are going to be looking at what are called redox reactions. Redox simply stands for oxidation and reduction reactions, so they just abbreviated it. So before we can start talking about what redox reactions are, we need to understand fundamentally what an oxidation versus a reduction reaction are. So when you're thinking about oxidation, oxidation is simply when electrons get lost when you go from the reactants to the products. And the reverse of that is what we call a reduction reaction, where you're actually gaining electrons when you're going from the reactants to the products. So if we take a look at the example under oxidation, we see that our reactant in that situation is going to be aluminum, and our products are going to be the aluminum ion plus 3 electrons, because remember, on the left and right hand side of your chemical equation, you always have to have things balanced. So if we have a neutral atom on one side of the reaction, then we need to have charges that cancel out on the other side of the reaction. So if we're forming the aluminum ion, we need to also show that there are 3 electrons being lost in the products because it needs to cancel out. Same thing when we look at our reduction example. So here we're looking at a molecule of nitrogen reacting with 3 electrons. And when the nitrogen molecule reacts with the 3 electrons, we end up with a nitrogen ion in our product side. So there are 2 helpful ways to help you guys remember the definition of oxidation and reduction reactions. So the first one is LEO goes GR, and simply what that means is the loss of electrons is oxidation, so LEO goes GR, so the gain of electrons is reduction. So that's one way you can remember it. Another common saying that's used is oil rig. So oxidation is loss, and remember here it's talking about loss of electrons. And reduction is gain, and again, remember we're always talking about the electrons. So reduction is the gain of the electrons. All right, so in order to determine our redox reactions, we need to start by writing a net ionic equation. And we know from our net ionic equations video that generally they're written with double replacement reactions, but they can also be written with single replacement reactions because really they can be written with anything that has any aqueous reactants or products. Let's take a look at our example here. We have silver nitrate reacting with copper. So this should really tell us that the silver nitrate is going to be aqueous, and that this copper is really copper 2. So let's take a look at what that balanced equation would look like. So our silver nitrate is going to be AgNO3 aqueous plus solid copper, and then we use our activity series to see if that copper can replace the silver. And since copper is higher on the activity series than silver is, it can replace it. So you end up with CuNO3 2 aqueous. Remember, the product of a single replacement reaction, the compound, is always going to match the compound's state of matter from the beginning, plus solid silver. And then we also need to go through the balancing. So since we see 2 nitrates on the product side and only 1 nitrate on the reactant side, I'm going to add a 2 coefficient in front of the silver nitrate. And because I've added a 2 in front of the silver nitrate, I need to add a 2 in front of the silver on the product side. So now we need to go through the process of writing our net ionic equation. So remember, for your net ionic equation, you're going to break everything that's aqueous down into the ions. So we know we've got 2 silver ions plus 2 nitrate ions plus a copper, which is solid, to produce a copper 2 ion plus 2 nitrate ions plus 2 silvers, which are going to be solid. So when I take a look at this, the only spectator ion here is going to be the nitrate. So we're going to go ahead and remove the nitrate and write what we're looking at here, remember, this is what we call the total ionic equation. And now that we're going to remove those spectator ions, we're going to have our net ionic equation. So we'll have 2Ag plus Cu to produce Cu2 plus 2Ag solid. All right, So now we have to look at what's happening to each part of the reaction. So starting with the silver ion, we see that we've got 2 silver ions that are going to become 2 stable atoms of solid silver. So here, in order for us to balance this equation, we see that we have 2 positive charges on the left-hand side, on the reactant side, and no charges on the product side. So we have to add in 2 electrons here to cancel out the 2 positive charges from the silver ion, and that would help us balance this equation. And we're going to come back to what that means in just a second. So let's take a look at the next example where we're looking at the copper metal. So we've got the copper solid forming a copper 2+ ion. And in order for us to balance this equation, we see that we've got 2 positive charges on the product side and no charges on the reactant side. So we're going to add our 2 electrons to the product side so that we can balance those charges out. So now, looking at this information, we have to determine which element is being oxidized and which element is being reduced. So remember that saying, we've got Leo the lion goes grr, so the loss of electrons equals oxidation, and grr for GER, the gain of electrons equals reduction. So now we have to figure out which one's happening where. So in the silver ion, we see that they are gaining electrons between the reactants and the products. So if it is gaining the electrons, we know that the silver ion is being reduced. And when we look at which element is being oxidized, the oxidation is where the electrons are being lost. Remember, it's lost between the reactants to the products. So here we see the electrons being lost because they are part of the products on the right-hand side. So the element that's being oxidized is the copper. So not only can we predict what's happening in a redox reaction, but we can also determine what is called the oxidation number of different elements. And those elements could be by themselves, what we call the elemental form, or they could be part of a formula. So let's take a look at some common oxidation numbers here. So the first rule is that the oxidation number for an atom in its elemental form, so an atom that is just by itself, is always going to be 0. So S8, remember sulfur is a polyatomic element, so when it's by itself it appears in 8s. Since that is in its elemental form, it is always going to have an oxidation number of 0. Iron, another example, if it's iron by itself, it'll have an oxidation number of 0. When we think about monatomic ions, so remember mono meaning 1, so 1 ions, so single atom ions, the oxidation number is going to be the charge on that ion, so the oxidation number of S2- is -2. The oxidation number of aluminum 3+ is +3. And then these ones are pretty easy because there's things that we've already learned. The oxidation number of all group 1A elements or metals, remember these are alkalis, is going to be +1, and the oxidation number of all group 2A metals, remember these are the alkaline earth metals, is going to be +2. So these are just some other common element oxidation numbers. So hydrogen actually has 2 possible oxidation numbers because hydrogen is special. So it can have an oxidation number of +1 or -1, just depending on what it is bonded to. Oxygen also has 2 possible oxidation numbers. It could be -1 if you're thinking about it in a peroxide, but those are pretty uncommon. Generally, you're going to think about oxygen having an oxidation number of -2. And the oxidation number of fluorine is always going to be -1. So when we're looking at trying to determine the oxidation number of an element within a compound, the thing that we need to remember is that the sum of all the oxidation numbers of all the atoms or ions in a neutral compound is 0. And so we're going to use that to kind of work backwards to determine the oxidation numbers. And we know that also the sum of all of the oxidation numbers of all the atoms in a polyatomic ion is going to equal the charge on that poly. So let's take a look at what I mean by that. All right, so let's take a look at how we can determine the oxidation number of elements within compounds. So in this first example, we're looking at trying to figure out the oxidation number of sodium within the sodium sulfate compound. So the first thing you want to check is whether or not the compound you're looking at has a charge. And remember, charges are always located in the upper right-hand corner. And since there is no charge here, we know that it has a neutral charge, and that neutral means 0. So we know that that neutral charge of the compound is going to equal the sum of all of the oxidation numbers of things within it. So we know that we have 2 sodiums, and we're trying to figure out what the oxidation number of the sodiums are. So we're going to leave them as 2Na. And then we know that we have a sulfate ion, and that sulfate ions have a charge of -2. So now we're just going to solve for Na. We're solving for what that oxidation number is. So remember, when you're adding a negative number, it's the same thing as if you're subtracting it. So we have 0 equals 2Na minus 2. So we're going to add 2 to both sides. And then I'm going to bring this up here. So I have 2 equals 2 sodiums. So then to get sodium by itself, I'm going to divide by 2. So we know that plus 1 is going to equal the oxidation state, or the oxidation number, for sodium. All right, let's take a look at our next one. So here we're looking at bromine. And it's bromine by itself, and we know that bromine is diatomic, so we're looking at Br2. And since bromine is in its elemental form, we know that it is going to have an oxidation state of 0 because it's in its elemental form. All right, so last one that we're going to try together. So here we're looking at the manganate, we're looking at the manganese atom and the permanganate ion. So when we write out that permanganate ion, we know that it is MnO4 minus. And since this is a polyatomic ion, the sum of all of the atoms within this ion have to equal the charge of the poly. And so since the charge here is -1, we know that the sum of everything is going to equal -1. So -1 is going to equal whatever the oxidation number of permanganate is, plus 4 times the oxidation state of oxygen. And remember, the most common oxidation state of oxygen is going to be -2. So again, when we're solving for this, we have -1 equals Mn minus 8. So I'm going to add 8 to both sides. So the oxidation number for manganese in the permanganate ion is going to be +7. So now I'm going to have a couple of other examples that I want you guys to use these steps to try and determine what the oxidation number of the examples given are.